And welcome to the Lesson 19-1 practice video. Thought I'd provide some assistance for those needing a little help with the Lesson 19-1 practice. So let's get going. Number 8 says, in the figure, triangle XYZ is a right triangle, and line W or YW is an altitude to the hypotenuse. Suppose you know that the measure of angle X is 62 degrees. What other angle in the figure must also measure 62 degrees? So what we're learning in this lesson, and we'll definitely use this in future lessons, is that when an altitude is drawn, which is a segment from a vertex perpendicular to the opposite side, and you see that it's perpendicular by creating a right angle, that altitude divides our original triangle, in this case, triangle XYZ, it divides it into three similar triangles. And remember, similar triangles are triangles that have corresponding angles congruent. So if we know that there are corresponding angles that are congruent, we should be able to find other angles besides X that are 62 degrees. Here's my advice on this. Draw the right triangles in a similar fashion we did on number 7, the check your understanding, such that each triangle has the right angle in the lower left position. So that's what I'm going to do. So I'm going to start with our largest triangle, triangle XYZ, where our right angle is in the lower left position. So that'll be Y. ZY is our longest leg of the right triangle, so we'll put Z up here. Therefore, this will be X. And they've already told us that X is 62 degrees, so let's go and add that in right here next to our angle X. Now I'm going to draw our medium triangle. Now looking at the medium triangle, W, or vertex W, is where the right angle is located. So when I draw my medium, I'll draw it a little bit smaller, just so it's somewhat to scale. I'm going to put W here at the right angle. And WZ is our longest leg of this medium triangle. So Z is still up here at the top, and therefore WY is our short leg of the medium triangle. And last but not least, we're going to look at the small triangle here. Again, we'll draw it such that it's a little bit smaller and the right angle is in the lower left position. Again, vertex W is the right angle for our small triangle. In this case, WY is the longer leg of triangle WXY. So Y will actually go up here, and therefore what's left is X will go here. So they want us to know what other angles had to be 62 degrees and why. So if these three triangles are in fact similar triangles, then corresponding angles are congruent. And if we know this angle is 62 degrees, then these two angles combined have to be 90 because 90 degrees is already taken up by that right angle. So I believe that will be 28 degrees here. Doesn't hurt. They don't really want to know what angles are 28 degrees, but it wouldn't hurt. So the reason we put it on these similar positions is so we can see how angles correspond. So this angle is 28, this angle will be 28, and therefore this angle will be 28. This angle is 62, this angle will be 62, and this angle is 62. Now, because vertex Y in our original diagram is actually originally the right angle, we have to get very, very specific about what angle this actually is, because multiple angles share vertex Y. So we can say angle WYZ or angle ZYW. Again, angle ZYW or WYZ. This angle right here is our other angle besides X, because if you notice, angle X pops up twice in the larger and smaller triangles. This is our other angle that is 62 degrees. And again, we can't call it angle Y because multiple angles share vertex Y. So we'll say angle WYZ, we'll say the measure of angle WYZ is 62 degrees because corresponding angles of similar triangles are congruent, and angle X is congruent to angle WYZ. That seems to be a pretty good explanation. We're mentioning that these triangles created by the altitude are similar triangles, and similar triangles have corresponding angles that are congruent. And we even mentioned that angle X is congruent to WYZ. Now let's move on to number 9. Given the figure with right triangle, there we go again, DEF, they tell us that FG is perpendicular to DE. So can you guess what we're going to call FG, what type of segment? The altitude. If it comes from a vertex of a triangle perpendicular to its opposite side, it's called an altitude. So that means we should have 3 similar triangles here, a small, medium, and large, if you will. So it says complete the similarity statement given that measure of angle E is 25 degrees, DF is 8, and DE is 17. So I'm going to do this in a similar fashion to the last one. I'm going to draw a large, medium, and a small right triangle, all with the right angle in the lower left position. So in terms of our large triangle, DEF, F is the right angle vertex, with FE being the longer leg, so E will be up here, and FD will be our shorter leg, so D will be here. And then in terms of our medium triangle, which would be triangle FGE, G is our right angle vertex, with GE being the longer leg, so E will again still be up here, and therefore GF is the shorter leg down here. And last but not least, the small triangle, G again is the right angle vertex, where GF is the longer leg, and therefore DG is our shortest leg. And I see that I just messed up here. So this would be G and then D, and then F would be up here. So they tell us that the measure of angle E is 25 degrees. So that means that this angle right here, being the exact same angle, is 25 degrees, and therefore angle F in the small triangle is 25 degrees. Remember, these two angles are complementary angles because the 3 angles of any triangle add equal 180. So if 90 degrees is already taken up here, there's only 90 left for these 2 angles. So 90 take away 25 will be 55 degrees. Therefore, these 3 corresponding angles will be 55 degrees. Just adding a couple. I don't even know if this is going to help us, but it doesn't hurt to use the information we have. And DF is 8. So anywhere we have DF, which we also have it here, and DE is 17. DE is 17. So 17 here, and I believe that's the only place that DE is a part of a triangle. So it says complete the similarity statement. Triangle DEF is similar to triangle FEG. Notice how I did that. I started with vertex D because that's what they started with. DEF will be similar to triangle FEG. Doesn't matter if you listed the medium triangle second or last. It just makes sense if we start large, then we'll go medium, then small. And so if it's triangle DEF similar to triangle FEG, it would be similar to triangle DFG. Now, one of the reasons we really like writing similarity statements is the order tells us which parts are corresponding, such that DE in the larger triangle corresponds to FE in the medium triangle. And that's where it gets a little bit tricky, because if you notice, the large triangle also has FE. It's because these segments are acting as 2 different types of segments. For example, DE is the hypotenuse of the larger triangle. FE is the larger or the longer leg of the largest triangle, but it's also the hypotenuse of the medium triangle. So that's why these similarity statements look a little bit weird, because these segments are acting as 2 different types of segments depending on which triangle we're looking at. So that's why we like these statements, and that's why we like drawing this visual. Number 10 says use the figure in item 9 to find each of the following measures. So I assume we're going to be using all the measures that they gave us from item 9. So measure of angle D, we already figured out, is 55 degrees. So we did a lot of legwork there already. The measure of angle GFE, which would be right here, is also 55 degrees. Segment FG, we don't know, so we'll come back to that. Let's go and finish out our angles because we did find those. And angle DFG is 25 degrees. So we are tasked on 10 to find the length of FG and also FE, which I believe, do we have FE? No, we don't. So we need to find these two segments here. So because we're dealing with similar triangles, corresponding sides should be proportional. So we should be able to write proportions. And since we have this drawing here, it'll make it very easy for us to write those proportions. So let's start by solving FG. You can either look in the diagram or up here, and we see that FG corresponds to EG. FG of the small triangle corresponds to EG of the medium triangle, so we could figure that out here. Or if you look at the diagram, which I really lend to looking at, is we see that FD is in a similar position to GF. So we could actually say that these parts are corresponding. The only problem is, if we write that these parts are corresponding, we don't have a full pair of corresponding parts to create a proportion. So let's tackle this a little bit differently. Let's see if there's any other information we're actually missing here. So the interesting thing about this problem is that the two sides that we're looking for technically on the medium triangle correspond to these two sides here, but again, we would have two missing values in our proportion. Something I just realized is staring at me right in the face. If we know two sides of a right triangle, we can find the third using the Pythagorean theorem. So let's do that now to find the third. So even if we don't use the similar triangles at all, we can find this third side because we have two sides of a right triangle. So 17 being our longest side, opposite of the right angle, that's our hypotenuse. So 8 can either be A or B in the Pythagorean theorem. So we'll say 8 squared plus, we'll say we're solving for B, so we can assume EF is lowercase b, and C squared is 17 squared. So 8 squared is 64. 17 squared is 289. Subtract 64 from both sides. We get b squared equals 225. To undo b squared, or to get rid of this exponent, we're going to take the square root of both sides. And we'll get b equals, fortunately for us, 225 is a perfect square. B equals 15. So now that we have all three sides of our larger triangle, we won't have as many missing values in our proportion. So let's continue on now. So we can say that 8 corresponds to GF. And since we just found that EF is 15, we can also put that value here. So I don't even know why I didn't put that together, that we could have found EF from the beginning using the Pythagorean theorem. Just got a little ahead of myself with these similar triangles. And so now on this triangle, we have one side that corresponds to one side from the larger, and we're looking for another side, and we do have that corresponding side from the larger. So there's our proportion. So we'll say that FG corresponds to FD. FG corresponds to FD, just like EF corresponds to ED. Just like EF corresponds to ED. Going to do some replacing. FG, we'll call it X, since we don't know the measure. FD will replace with 8. EF will replace with 15. Found that using Pythagorean theorem. And ED will replace with 17. I typically use cross multiplication here, although there are other ways to do this that some of you are figuring out. So 15 times 8 is 120. X times 17 is 17x. Divide both sides by 17, and x will be approximately, I have 7.058. So we'll round to the nearest tenth, so it'll be 7.1. So again, we found the missing side of this large triangle EFD using Pythagorean theorem, because we use Pythagorean theorem when finding a missing side of a right triangle. If you're still uncomfortable with it, don't worry. We are going to see more examples of Pythagorean theorem in activity 20. And then we use, once we had all three sides of this triangle, we use the fact that corresponding sides are proportional, and we wrote a proportion to find the missing side FG. The last question asks us, or states, that triangle HIG is an isosceles right triangle. If it's isosceles right, it means that it has two congruent sides and one right angle. It says make a conjecture about the two triangles formed by drawing the altitude to the hypotenuse. It says write a paragraph proof to prove your conjecture. So I'll help you get started here. You don't have to write a paragraph proof. You can write a 2-column proof or a flowchart proof, whichever one you're more comfortable with. But we're going to start by drawing the altitude. So it says drawing the altitude to the hypotenuse. So that means this is the hypotenuse of a right triangle. So we're going to start from this vertex J and try to draw a perpendicular segment to this hypotenuse HI. And it says make a conjecture about the two triangles formed by drawing the altitude to the hypotenuse. So let's think about this for a second. We'll just kind of think this one out, not necessarily write a proof here. If triangle JIH is an isosceles triangle, that means this side has to be congruent to that side. Two sides have to be congruent, and it definitely can't be the hypotenuse, because the hypotenuse has to be the longer side of a right triangle. Well, if these two sides are in fact congruent, then this angle has to be congruent to this angle. Angles opposite of congruent sides actually have to be congruent, because angles determine opposite sides. So let's think about this. If we know that triangle JIH is a right triangle, an isosceles right triangle, and these two angles are congruent, well, angle J from the original triangle is 90 degrees. These two angles have to be the same measure and sum to equal 90 degrees. So 90 degrees divided by two angles evenly will be 45 degrees. So this triangle will have a 45 degree angle, and this triangle will have a 45 degree angle. And now that we divide it into two smaller triangles, if this angle is 45 degrees, then this angle IJH, also has to be 45 degrees. And so does triangle HI or HJ. I guess we could call this X if you want. Angle HJX is also 45 degrees. So something we could say is that these two triangles are congruent triangles, but they're also isosceles right triangles as well. So interestingly enough here, when we take a isosceles right triangle and draw an altitude from the right angle to the hypotenuse, it actually divides it into two smaller right isosceles triangles. And I encourage you to continue that pattern. Maybe draw an altitude from X to this side and consider, is it going to keep creating isosceles right triangles every time we draw that altitude? So you can write a paragraph proof, a formal 2-column, or a flowchart proof if you prefer. But it's really just seeing what's going to happen to an isosceles right when we draw that altitude, creating two similar isosceles right triangles. Well, that's the lesson 19.1 practice. I hope that helps your understanding a little bit. And always check the answers. There is an answer key for this practice as well, if you would like a more paragraph proof style of this reasoning here on item 11. Thank you for watching.